Okay, so this next exercise is again about Sn, the symmetric group of degree n, and here n is at least 3, and we are considering a subset H of Sn defined like this. It consists of all permutations beta in Sn such that the value of beta at 1 is either 1 or 2, and also the value of beta at 2 is also either 1 or 2. We have to prove first of all that this H is a subgroup of Sn, and then we also have to determine its order. So let's see the subgroup thing first. It seems like the way this H has been defined and the way this thing has been written, it has many conditions, right? So if we work with these conditions separately, there will be many cases. So let us see if we can compress things a little bit. Note that H can also be written like this. It is the set of all permutations beta in Sn such that the image of the set consisting of 1 and 2 under beta is a subset of the set itself. Is it really true? Let's just first see that. Say you see, at least one thing is immediately true from these conditions, that whatever the case may be, whether beta of 1 is 1 or it is 2, we of course have this. Similarly, we also have this thing. So definitely we will then have this. Because this is after all nothing but this set, that is this set is by definition of direct images of sets under a mapping. This set is just this. So because both these elements are elements in this second set, so this is a subset of this. So that means if we are choosing a beta from this given definition of H, then that beta also satisfies this containment relation. But is the converse true? Because if the converse is not true, then we cannot say that H is equal to this. With only this much, we can just say that H is a subset of this. But the converse is of course also true. Why is that so? Because you see, if we are starting from this containment, then that means what? That means this set is contained in this, which then implies that this and these two conditions are true, and that is just the same as saying that beta of 1 is 1 or 2, and also beta of 2 is 1 or 2. So it's justified that we have written H equal to this, that is justified. Okay, now it will be somewhat easier for us to show that H is a subgroup of Sn. So first of all, we have to make sure that H is non-empty. That of course we will show by demonstrating that the identity element of Sn is in H, that is the identity permutation. Note that for the identity permutation E in Sn, E of 1, because it's the identity map, E of 1 is 1 and E of 2 is 2. So that means E is actually satisfying these conditions. Hence, E belongs to H. To conclude this, however, only this, we don't really need this, but now we will need this. A slight reformulation of H, I mean a redefinition of H in a slightly different way. Now, let alpha and beta be two elements in H. Then by this, the alpha image of this set consisting of 1 and 2 is contained in this set, and the beta image of this is also contained in this set. Hence, now because direct images respect inclusion, what that means is that if you have, say, a function, any function f from some set x to another set y, and say you have two subsets A and B of x which are related to each other by a relation like this, that A is a subset of B, then the images of these sets are also similarly related. We express this by saying that direct images respect inclusion, that is, they behave well with respect to inclusion. So because of this thing, we can now apply alpha on both sides of this inclusion. That is, you think of beta of 1, 2 in place of A and 1, 2 in place of B, and in place of F you think of alpha. Then we get what? Alpha of beta of 1, 2. Okay, we can, let me just write one more step so that in this calculation itself everything is included. Hence, the alpha beta image of 1, 2, this of course means composition of mappings, that is the binary operation in Sn. This is equal to alpha of beta of 1, 2 because it is composition, and then by that thing that I said just now, this is contained in alpha of 1, 2 because beta of 1, 2 is contained in 1, 2 as a subset. So their alpha images are also similarly related, and then again you use this. So this in turn is a subset of 1, 2. So that means just like alpha and beta, the image of this set 1, 2 under alpha beta is also contained in 1, 2. So alpha beta belongs to H, and that's just enough for us to conclude that H is a subgroup of Sn, because we are in a finite group. So they're just if you show that a non-empty subset is closed under the binary operation, then it is a subgroup. Inverse exists for every element in the subset, that need not be shown, that follows from this itself. since Sn is a finite group, this implies H is a subgroup of Sn, and then we have to find the order of H. For any beta belonging to H, we have exactly two possibilities. And those two possibilities are this: beta of 1 is equal to 1 and beta of 2 is equal to 2. So this is one. Okay, let's just call this 1 and 2. Beta of 1 is equal to 2 and beta of 2 is equal to 1. Okay, why is it so? Keep in mind that beta is not just any function, but beta is a permutation. So beta is 1 to 1 and onto. The conditions that define the subset H, that tells us that beta of 1 and beta of 2 are again either 1 or 2. So if beta of 1 is 1, then beta of 2, since it has to be either 1 or 2, it is forced to be 2. It cannot then again be 1. That is, if beta of 1 and beta of 2 are both equal to 1, then beta fails to be 1 to 1. And that creates, because then it's not a permutation. Similarly, if beta of 1 is 2, then beta of 2 is forced to be equal to 1. And what about the other symbols? What is the behavior of beta on the other symbols? That is not restricted in any way. So elsewhere on this set of symbols, elsewhere means in this region, beta actually can be any, it can permute the remaining elements among themselves in any possible way. Okay, so how many elements are here? N minus 2. So they can be permuted among themselves in n minus 2 factorial ways, giving us that many betas. But at the same time, independent of those things, these two possibilities are also there. So that means in this part of the set of symbols on which the permutations are acting, there are two possibilities, and on this part there are n minus 2 factorial possibilities. So you have to take the product of these two things. That will give you the total number of elements in H. So let us write these things. We have to carefully write something so that this is explained. for okay, not like this, the remaining symbols are permuted among themselves by beta. And why among themselves? Because the effect of beta on 1 and 2 already keeps that effect trapped within this region that has 1 and 2, and the effect of beta on the other part of the set of symbols, that whatever is happening is independent of whatever is happening with 1 and 2. So that's why they are permuted among themselves by beta. Hence, there are n minus 2 factorial ways of permuting the symbols by beta. Consequently, let's just write the conclusion. If you want, you can drag it a little bit further, writing something else, but eventually you have to write the order. So that is the order of this subgroup, and this is the solution. Next, show that in S7 in the symmetric group of degree 7, the equation x squared equal to this 4 cycle 1, 2, 3 and 4 has no solutions. But the equation x cube equal to that same 4 cycle has at least two solutions in S7. So let's see the thing. So first of all, we want to show that this equation is not solvable for x in S7. What that simply means is that there exists no permutation x in S7, which if you put here will give you this 4 cycle. So to see that, let us first of all see what the possible orders of x are. That is, if x is some element in S7, say which satisfies this, then from this equation we will be able to say something about the possible order of x. So let us first do that. Suppose, so we are supposing something and we will derive a contradiction. Suppose there exists some x in S7 such that its square is this 4 cycle. Then the order of x divided by the greatest common divisor of the order of x and this exponent 2. We already know that this is the formula for the order of x square. Using this relation or this formula, we can find the order of an integral power of some element in terms of the order of the element. And this is equal to, according to our supposition, this is the order of this 4 cycle, and the order of the 4 cycle is of course 4. Okay, so we seem to have got one relation from which we will be hopefully able to say something. So this thing equals 4. Now since the greatest common divisor of this is 1 or 2, we have, okay, the first question is, why is this 1 or 2? You see, the GCD of two integers of course is something that has to divide both of them. So that means the GCD should divide 2, but at the same time the GCD by definition is a positive integer. So there are only two positive integers that divide 2, 1 and 2. That is because 2 is a prime number. That's why we are having this. So because this is either 1 or 2, so we can now actually exactly say what the order will be in these two cases. So when the GCD is 1, the order is 4, and when the GCD is 2, the order is going to be 8. Okay, so if there is some element x that satisfies this equation in S7, then its order has to be either 4 or 8. Now we look for elements in S7 of order 4 or 8. S7 has many elements, right? It has 7 factorial elements. So of course we are not going to look at all of them one by one. That is practically impossible. But we don't really need to look at the individual elements, but rather we need to look at their cycle structure, and that too, the lengths of the cycles. So essentially that requires us to first of all look at the partitions of 7. So let's just do that. The partitions of 7 are, okay, so now I have the partitions here with me. Let me write them in a somewhat readable form, although it will take some space, but it's okay. 7, one of them is of course 7, then 6 plus 1, 5 plus 2, then 5 plus 1 plus 1, 4 plus 3. There is of course some pattern in which you can in fact find this partition, the partitions. We are not going to deeply into that. We just take this thing as a given information and we just use it. 4 plus 2 plus 1, then 4 plus 1 plus 1 plus 1. Partitions of integers is an extremely vast subject, and there we have many things found by Ramanuja. Then 3 plus 1, and 3 plus 2 plus 2, okay, writing these things down, I can already see some pattern. Do you see that? The parts, the summands in these sums, they are getting smaller and smaller. So a part of the whole sum is getting to that other side, and there slowly these things are decomposing, and the decomposition is starting from the rightmost side. Here 3 has become 2 plus 1, 1 cannot be further decomposed, so the next one is 2, that has then suffered a decomposition, 1 plus 1. Similarly here, so you start with this, then you have another one. Well, of course, okay, we can also consider 3 plus 2 plus 1 plus 1, which has not yet appeared. Oh, but that has appeared here. But anyway, that is just my guess. That's how these things are being found. Then this is also 7. And finally one more where everything is 1. 4, 5, 6, 7. Okay, let me just see 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 4 5 6 7 8 9 10 11 12 13 14 15. Okay, so these are all the partitions of 7 and each one of them corresponds to a cycle structure of any permutation in the group S7. For example, 7 corresponds to a 7 cycle. Six plus 1 corresponds to a 6 cycle. Actually a product of a 6 cycle and a 1 cycle, but since we do not write 1 cycles or show them because they show something which is kept fixed by the permutation, so we usually do not write 1 cycles, but still for the sake of showing how the correspondence is there between cycle structure and partitions, so we are writing like this. Just like that, 5 plus 2 corresponds to a product of a 5 cycle and a 2 cycle. And the others of course also correspond to some cycle structures. Now there are of course many 7 cycles, but so far as order is concerned, all of them have one order, which is 7. When we come to 6 cycles, the order is 6. When we come to a product of a 5 cycle and a 2 cycle, the order is, you already know how to find the orders of permutations. The order is the LCM of the cycle lengths, that is 5 and 2, this is 10. Here the order is going to be what? 12. Here the order LCM of 4 and 2 is 4. Here also the order is going to be 4. Okay. Here the order will be 3, 6, 6. We are taking LCMs, okay. 3, 2, 2, 2, 1. This partition specifically corresponds to exactly one permutation, which is the identity mapping, which is just a product of 7 1 cycles. That means it does not change anything. So these are all the possible orders, and among them you already see that these cases are automatically ruled out. Only these 2 cases remain. Okay, so we can conclude like this now. So having written all these partitions, each such partition, or each partition can just simply write corresponds to a cycle structure in S7 and hence corresponds to, you don't actually need to of course write these things and circle them, show, you don't have to do those things, you just have to write the partitions and then continue from here, and hence corresponds to the order of all the permutations in S7 with that particular cycle structure. Each okay, so that's what we have written. Hence the possible orders, okay, we now have to wrap these things up, but let's just for once write the orders that we have written here on this side here also. We have 7, then 6, then 10, 12 and 4. Okay, so now we can write the orders here. I think I could use some ink now itself before it's too late. Hence the possible orders are these. 1, then 2. Let us also strike these things out. Okay. Then we also have 3. Then 4 is there. Then after that we have 6 and 7, then 10 and 12. Okay, so but we need orders 4 or 8. So that means order 4 elements are of course there, but I actually don't have the partition with me, no? The partitions which give rise to cycle structures and which in turn give rise to this order 4, there are 2 types of partitions. So the elements in S7 of order 4 are, or let's just write like this: each element in S7 of order 4 is either a 4 cycle or a product of a 4 cycle and a 2 cycle. Why? Because you go back to those partitions, you will understand why. or a product of a force cycle and a disjoint. Disjoint, of course, when we are talking about cycle structures, the cycles in a single permutation are disjoint cycles. Okay, now not just any force cycle, but the kind of force cycle for which x square is equal to this. So evidently, whatever force cycle x is, the symbols in it cannot be anything else. That is, the symbols will be these symbols only, nothing else, because if you have something else, then that something else will still stay when you form x square. So that means this will again be another possible partition of these four symbols. Now, how many such force cycles are there? Since x square is equal to this, if x is a force cycle, then these are the possibilities. We are now actually going to write all the possibilities. Okay, how do you write all the four cycles? Keep in mind that this is not an ordinary permutation but a cyclic permutation. That is, you should actually not bother about the positions of all the elements. For example, this cycle is the same as this cycle 2, 3, 4, 1. But if you just simply write these two finite sequences without saying that they actually represent some cycles, then they are different permutations, because the first element here is 2, here the first element is 1. But because only the cyclic structure has to be preserved, the cyclic order has to be preserved, so the thing here you have to do is you fix any one symbol and then permute the others. That gives you all the cyclic permutations. So that is why we are going to keep one fixed and in the first place itself and permute the others. That will actually give us all the four cycles which involve these four symbols. So say another one will be 1, 2, 4, 3. Why is it a different force cycle? Because under this force cycle, the image of 3 is 4. But under this one, the image of 3 is 1. So they are different permutations. Then 1, 3, 2, 4. 1, 3, 4, 2. Then 1, 4, 2, 3, 1, 4, 3, 2. Why are there 6? That is because we have kept one of them fixed and we are permuting the others. There are 3 remaining, so 3 factorial is 6. Now you look at all of them one by one and see whether their squares are equal to this. We will find that actually none of them satisfies this equation. That we can do mentally. We need not write anything for that. We will just simply mention that it is so. that none of these possible 4 cycles satisfies that above equation. However, none of these 6 4 cycles satisfies this. Let us just see for once why. Okay. So what do we need here? We need x square to be equal to this. So that means if we take for example the square of this itself, that square will first of all take 1 to 2 and then 2 to 3. So that means if you calculate the square of this one, the image of 1 will be 3. That's not what we have here. So that means this is ruled out, the first one. The second one is also I think ruled out, because if you take the square of the second one, it sends 1 to 4. First it sends 1 to 2 and then another time you apply it on 2, that is sent to 4. Here 1 is not sent to 4, 1 is sent to 2. So this second one is also ruled out. Similarly, you will see that the others are also ruled out. Maybe if you take the square of the other 4, one of them will actually give you 2 as the image of 1, but in the other parts it will not match with this thing. Okay, so that I leave to you. It's just 6 of them, so you can easily see. Similarly, if x is a product of a 4 cycle and a disjoint 2 cycle, then x is of the form x equal to y z, where y is one of those 6 4 cycles listed above, that is this, and z, we don't actually need to mention anything more. Z will be a 2 cycle involving 2 symbols which is not among these 4, 1, 2, 3 and 4. So because these cycles themselves fail to give us this when they are square, so here also we will not actually get that thing that we want. This equation will not be satisfied. And why is that so? Because you see, we are going to continue after this, okay, but let us just see what will happen in this case. In this case, if you calculate x square, then that is actually equal to y square z square. Why? Because y and z being disjoint, disjointness plays a role here. Being disjoint, they commute, so that's why x square becomes y square z square. But because z is a 2 cycle, so actually x square is y square. So again we come down to squaring these things which do not give us this, so that's it, game over. Okay, so now we continue. Here also Here there will be many more elements than we have here, because Z is also involved, and who knows how many other symbols are there besides this 4. But in this calculation shows that that does not matter. We anyway are not going to get what we want. So we do not drag this matter any further and directly write the conclusion. Here also there is no x that I was saying who knows how many other symbols are here. Of course we will know how many other symbols are there. Besides 1, 2, 3 and 4, you have 5, 6 and 7, because we are in S7, right? We should not forget that. That satisfies but still that gives us some choices for Z. Thus, our initial supposition is wrong, which was just simply the statement that there is such an X. That is, the equation cannot be, what have I written here? Cannot be solved for x belonging to S7. So that is just one half. There is that other half also, which asks us to show that if this 2 is replaced with 3, then actually there are solutions, and in fact there are at least 2. So for that we just simply write 2 such solutions and just settle the matter. Note that the permutations, one of them is, do I have it here or I forgot to write? Okay, 1, 4, 3, 2, and there is one more, both satisfy this. You just have to see one thing, that if you take the cube of this 4 cycle, then you get that 4 cycle. You just have to do things 3 times. When you calculate the cube, that cube first of all takes 1 to 4 and then 4 to 3 and then 3 to 2. So 1 goes to 2. Then 2 goes to 1, 4, 3. So 2 goes to 3. Like that, 3 also goes to 4 and 4 goes to 1. So cube of this is this. And when you calculate the cube of this, you just again use the fact that these two cycles are disjoint, so they commute, and that is why the cube of this product is the product of the cubes. And if you calculate the cube of this, because it's a 3 cycle, it will vanish, it will become the identity. So again you get the cube of this, which is this. So these are two different solutions to this equation. And tweaking things here, for example writing 5, 7, 6, you in fact get another solution. But we just had to show there are at least 2, and that's just it. So this completes the solution to this exercise. Let us solve one more. If AB and CD are distinct 2 cycles, in SN, prove that they commute if and only if they are disjoint. Oh, so this thing that we have used here in general has now been asked to we have been asked to show this in this particular case. The general case is also very easy if you think about it. But anyway, let's just see the solution. In general, we can say this: when two, not just cycles, when two permutations act on different symbols, that is, they do not act on the same symbol, then whether you perform one of them first and then the next, it does not actually matter. That is because, so what I am trying to say here is this: say you have two permutations f and g. After all, these are functions, no? Acting on some set of symbols which we normally denote by 1, 2, 3, 4 up to n. So the fact that f and g act on different symbols means that, by that we really mean that f traps the elements in this part itself, and g traps the elements of this part in this part itself, and even more importantly, f does not affect these elements at all. So this is where f has its action. This is where g is doing something. G does not do anything here, f does not do anything here. So now if you apply fg on these symbols, then say on what? On say something from here. Then first of all you apply g to this, which actually does not do anything to it. So that is the same as applying f. On the other hand, if you apply on this same thing GF, then you are first of all applying F, and F of course does something to this, but that something again stays in this region itself where G has no effect. So this becomes F of that thing itself. So it does not matter in what order we apply these permutations, and that's why Fg and Gf are equal. But here we are not going to use this general idea. We won't have to. We will just simply, because it's a very simple case, use the two cycles themselves. So it's given that these two cycles are actually distinct. Keep in mind that distinct is different from disjoint. Distinct means they are different two cycles, but a symbol may be common, but disjoint means no symbol, common symbol is there. Since AC is the same as CA and BD is the same as DB, distinctness of this and this implies we can assume, okay, this has become a long sentence, but anyway, we can assume without loss of generality that A is different from C. Okay, note one thing carefully. Oh, what have I written? A is different from, I think I have mixed things up. No, this is AB, sorry, and this is CD. From here I have written correctly, but here again I have made a mistake. Or did I not make a mistake? I am getting confused. AB and BA are the same, CD and DC are the same. So we can assume, because they are distinct, that A is not equal to C. Yeah, now it's okay. So now we have to prove that if they are disjoint, then they commute, and of course also the converse. If they commute, then they have to be disjoint. So if they are disjoint, then they commute. That I am just simply going to mention and not say anything about it. You have to, however, write in the solution the justification for it. That is, I am here now going to write clearly if they are disjoint, then they commute, but you have to write the justification, and that justification may be the thing that I showed here a few moments ago about F and G, or you actually show that in this particular case they commute. For that, however, you will need to assume the condition that B is not equal to D, okay, to give you disjointness. Anyway, I am not going to say anything more on that, so I am just simply going to write clearly if this and this are disjoint, then they commute. And now the converse. That is, if they commute, then they must be disjoint. However, we will not prove the converse itself, but rather its contrapositive. That is, if they are not disjoint, then they do not commute. That's what we are going to show, because it's easier to show that. But in that also you have to be quite careful about what you are going to do. Conversely, I mean, how you are going to start the thing, that there you have to be careful. Conversely, let this and this be not disjoint. So even in this simple case, there is a potential for us to get confused. Let's just write the things down. What are the things that we have? A is not equal to C. Okay, we already have this thing here. Also, A is not equal to B. Why? Because this is a 2 cycle, so different symbols should be there. At the same time, C is not equal to D, just like this one. Can we have A equal to D? That is another question. Can we have A equal to D? If we say consider A equal to D, does that create any problem? Still A is different from B, still A is different from C, and C is also different from D. In this case, D and A are the same thing, so there is no problem. Okay, so A can be equal to D. There is another possibility. Can we have B equal to D? In that case, we will have this. A and B are still different. B and C are actually C and D are different, but here B and D are the same, so it's okay. And A and C are of course also different. So you can see that there is no fundamental difference between these two cases. Why is that so? Because so what I am trying to say here is this. This can also be written as this, right? Like A comma B and A comma C. Here also we have A comma B. That A comma B can be written as B comma A, and here C comma B can be written as B comma C. So there is essentially no difference between these two cases, because in both the cases the way we have written the first elements, one of the elements involved is same in both the two cycles, and the three symbols that we see here, A, B and C, they are all distinct. The same thing here is also happening. So it's enough to consider only one of the cases. So let us just consider this one. That means A is equal to D. B, assume without loss of generality that A is equal to D, then we straight away calculate the products. AB CD now becomes AB, and because A is equal to D, so CA. And while calculating this type of products, we should again recall that we have to start from this side and then move to this side, because these are functions, right? So when you apply these functions on something, this one gets applied first and then this one is applied to that result. So this one sends A to C, and that C is unaffected then by this one. So A ultimately goes to C under this product. Then C is sent to A by this one, and then that A is sent to B by this second one. So C goes to B. What else do we have? B is unchanged by this one, and B is sent to A by this outer one. So B is sent to A. So this product is the 3 cycle. And the other product, changing the order, CA, A, B. Again, like before, A goes to B and B is unchanged by this, so A goes to B, B is sent to A, then A is sent to C, so B is sent to C. C is unaffected by this and C is sent to A, so C cycles back to A. And these 3 cycles actually are not equal. Why are they not equal? You see, the image of A under this one is C, but the image of A under this one is B, and B and C are different. Why? Because if B and C are also equal, then the 2 cycles become the same cycle and the distinctness is gone. The distinctness is always there. We have in fact considered 2 distinct cycles and started the thing, started the calculation. Then disjointness is there or is not there, that is different, that is extra. So since, let's just write that also, since B is not equal to C, ACB, this is not equal to ABC, which is equal to CTAB. So that means the cycles do not commute if they are not disjoint, or equivalently we have shown that if they commute, then they must be disjoint. So do not commute, and that's just it. Okay, so I'm ending things here itself. Tomorrow again we have real analysis, where this time convergence of series, that section is over. So now next we are going to consider infinite series of non-negative real numbers. There are some results about, particularly about those types of series, so that we will see tomorrow. So see you tomorrow with real analysis, infinite series, and I think in this next section there is a mention of that famous Riemann hypothesis, which is arguably the biggest unsolved problem in mathematics. The author says something about that, I think in this next section itself. So we will see that also. Even if I don't reach that stage, I will at least say something about that thing. So that's it. I wrap up for tonight. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.